Okay, so this is welcome to part 2 of our electrolysis work. To start off, we're just going to do a little review of the last lesson in the last video that you should have covered. So let's just jump straight into these questions, okay? So use the electrochemical series to predict the reduction and oxidation reactions for the following electrolytic experiments. Okay, so once again, like I went through for the last video, what I want you to do is make sure you list down all the possible reactants that can react. So we have molten potassium iodide with platinum electrodes. Now, our platinum electrodes are inert, they will not react. So we won't be including those in possible reactants. We have molten, and if you remember what that means is that we have pure potassium iodide. So there is no water present here in this cell. So what we do have though, potassium iodide, we have potassium ions and iodine ions in a molten solution, a molten ionic solution. So now we're going to use our series to determine what is undergoing reduction and what is undergoing oxidation. So our raw highest reaction in the forward direction is what we're looking at. So we had potassium ions and fluorine ions. I think it's going to be the potassium all the way down here. Yeah, so potassium undergoing reduction. Lowest reaction in the reverse direction. Find our iodine. Here it is all the way up here. Iodine, reading this reaction backwards, undergoing oxidation. So we'll write those ones down. So K positive plus an electron, give you K, and this is in a liquid form, and this is also in a liquid form because it's a molten cell that will retain that heat the whole time to produce a liquid metal. And then we have 2 iodine ions also in liquid form, oxidizing to form I2 in liquid, and 2 electrons is our oxidation reaction. Our K plus is undergoing reduction, so it is the oxidant or oxidizing agent, and our iodine undergoing oxidation is our reductant in this situation. Have a look at the next one, potassium bromide solution with copper electrodes. We have KBr solution, so KBr, that's BR, no, it's not KBr, sorry, KBr. So we have potassium ions, we have bromine ions in solution of water, and we also have copper solid because they're copper electrodes. It's important to make sure that you are clear on the states of the different substances you're looking at because that will depend on which way we do read this series. Highest reaction in the forward direction. Okay. Highest reaction. Let's go down. Remember, we've got water present this time. And that's oxygen. This half reaction if we have oxygen in the presence of water. So we're not using this one here. All the way down. It looks like we are using this water here. So highest reaction in the forward direction. The water is higher than the potassium, which is further down here. As the other possible reduction reaction or the other possible oxidant present in solution, but the water is a stronger oxidant in this case. Lowest reaction in the reverse direction. Let's go back up this way. We're looking for bromine, water, copper are our potentials. And looks like we've got 2 copper here undergoing oxidation. Okay, so write that in here. So we had, 2H2O liquid plus 2 electrons undergoing reduction to form hydrogen gas and hydroxide ions. And we had our copper solid as our strongest reductant undergoing oxidation to form copper ions in that solution. All right, we'll label again, just so really good revision anyway. The water is therefore undergoing reduction, so it's your strongest oxidant in this situation, and copper undergoing oxidation is your strongest reductant. Oops, reductant. Okay. So what I want to move on to is taking this chemistry and all the theory and just having a look at how it looks in application and how it actually does look in industry. So the first sort of demonstration that I would have taken you through, that I want you to click on the video just so you can have a look at how this actually works, is using what's called a Hoffman generator to electrolyze water. Okay, so we're once again using energy, using electricity to split water. What will we be splitting water into? I'm sure you probably already know, into hydrogen gas and oxygen gas. So it's something we hopefully I'll be able to show you when we do return to classes. It's a very unusual looking apparatus here. What I'd like you to do is have a watch of this little really quick YouTube video. It takes you through the demonstration of using the Hoffman generator. But what this cell effectively does is it's an electrolytic cell. It's connected to a power supply. We have our anode and our cathode present. We have electrodes, usually of platinum or carbon, within the Hoffman generator itself. And plugged into the electricity over a period of time, we get the water to be electrolyzed and produce hydrogen and oxygen. You can probably see quite clearly here that on the diagram we actually have a lot more hydrogen than oxygen. What that actually is, it's actually double the amount of hydrogen and oxygen, double the amount, and therefore that means double the amount in mole. And that makes sense because when we look at our full reaction, let's have a look at the overall reaction of water here. The overall electrolysis of water, if you were just going to, even if before we were doing redox reactions, you were going to say, okay, water splits into hydrogen and oxygen. What that means is once it's balanced, we require 2 mole of oxygen for every 2 mole of hydrogen for every 1 mole of oxygen. That's a normal regular balanced equation. Okay, that's something you would have done in year 10. However, what we can do is actually go back and have a look at this on the series and look at the 2 half reactions that would actually be occurring. Now, in this case, I'm using a hydroxide solution here, an alkaline solution, and so my half reactions chosen need to correspond to that. Okay. And I will show, let's have a look. So we can have a look at these half reactions. Our water undergoing oxidation and reduction. Now, we're not using this half reaction because this is in an acidic environment. So in the case, you can use an acid in the Hoffman generator, or you can use a base. Either one is appropriate. You're just requiring that electrolyte solution. So we've got our reduction reaction here. Sorry, wrong way, reading it this way. Our oxidation reaction here with the production of oxygen, and our reduction reaction here down below with the reduction of with the reduction to produce hydrogen gas. Let's go back. Okay, I just showed you the acidic one. What am I doing? Sorry, this one here, and our H2O in an alkaline environment, this one here. Okay, so we went through this last week when we looked at fuel cells, and we distinguished that when we are dealing with water particularly, we have to be careful as to what electrolytic environment we're in and to read the appropriate half equations. Okay. All right, so the next part of this is actually looking at some of the different types of cells that we will get in industry. And 2 common names we've already been through, molten cells versus aqueous cells. So I've talked about it before, molten or an aqueous cell, let's just start with aqueous, is what we've typically been looking at for the last few weeks, is where we have our cell and our redox reaction occurring within an electrolytic environment. And within that electrolytic environment, let's just basic in that electrolytic environment, we are talking about a solution of water which then has negative and positive ions dissolved in it, and that solution might be phosphoric acid, sodium chloride. It could be various different types of substances depending on the cell that we're looking at. But it is aqueous solution and where water is present. Because we're electrolyzing cells and you're forcing a chemical reaction to occur, what that also means then is water can potentially react therefore in that state. So what then has to happen sometimes in industry is the use of a molten cell. Now there's negatives to use of molten cells because to obtain a molten cell, what we need is really high temperatures. Because what we're actually doing is we're taking our electrolyte, and our electrolyte is an ionic compound because it has to have, generally an ionic compound, has to have positive and negative ions. You need to have a cation and an anion. Now, most ionic compounds at room temperature are solid crystal-like substances. Some of them require fairly large temperatures to actually to melt the substance into a liquid. The other thing as well, same thing with metals. Obviously, most metals have fairly high temperatures to melt them into a liquid. What you might remember, though, from year 11 is a lot of ionic compounds can be easily dissolved in water, hence why they're used in aqueous electrolytes. So water from molten cell, the molten cell is specifically designed to remove water. Talk about why that is the case in just a second. But to explain that really clearly to you, we're going to look at these two examples. So two cells. We're going to have a sodium chloride aqueous cell versus a sodium chloride liquid molten cell. So the L here means we are pure Na positive, Cl negative. Aqueous here, Na positive in H2O, Cl negative in H2O. Okay, so considering therefore we have sodium reacting and water and chlorine in this first one, let's have a look at the half reactions that are most likely to take place. So highest reaction in the forward direction, going all the way down here, we need sodium ions, water or chlorine ions, and it is water. So in this half reaction, in this cell here, the water here undergoing reduction is therefore a stronger oxidant than sodium, and water will inevitably undergo reduction well before sodium will. Okay, the strength here is quite significantly different. So we won't get any sodium solid or sodium metal being produced, which is potentially what is being tried to be, is ideally being made in this cell. If we look at the lowest reaction in the reverse direction, chlorine ions, water, and sodium ions. Here we go here. Have a look up here. Once again, we have water is the lowest reaction in the reverse direction that can take place. So water undergoing oxidation here, water is a stronger oxidant in this case, a stronger reductant, sorry. This is, as you can see, just based upon the E0 values as well as the position, water is slightly stronger than chlorine. Okay, so according to our series, water would electrolyze and produce oxygen. But what would also most likely happen is if this cell was made in industry, the cell's very unlikely to be placed under standard laboratory conditions. So what that means is what we would get is some competition at the electrodes. And it's also likely that we would get not only water electrolyzing, but most likely also chlorine to form chlorine gas. And both reactions would occur. So this concept is what we will look at in one of the experiments we'll do a little bit later on, and you'll be able to see how we get visibly more than one reaction actually occurring in electrolysis, particularly when we have half reactions like this that are really similar in strength. All right, so our chlorine and our water here are really similar reductant strengths in this electrolytic cell. Okay, So that's what the next few slides is about, taking you through some actual examples of certain cells that have been designed and why they have been designed a certain way. So the electrolyte of any cell, as we just spoke about, needs to be chosen really carefully. Can it have water in it? Depending on the degree of strength of the desired oxidant and the desired reactant. It will also depend on what else you can include in the electrolyte, what else you can include, or what the anode can be made out of, and what the cathode can be made out of as well. So everything needs to be designed really carefully. Before I look at specific cells, there's just one other little concept to go through, which is how we can also use our E0 values and our potential differences to work out, not to work out how much energy we're getting out of a cell. That's what we do for primary cells and what we've done for spontaneous cells. But we can do the exact same sum and look at the exact same potential difference. But what we're working at is what the minimum voltage required is for that cell to work. Okay, so rather than how much we're going to get out of that cell, we're looking at, well, how much energy needs to be put into the cell under standard laboratory conditions to get the reactant and the oxidant, the reductant and the oxidant actually reacting and producing our products. But you can actually use the series for this as well. What's probably worth also being mindful of is this concept of overpotential. So what basically that means, as you can probably imagine, there will be some small fraction of energy lost through the transformation of energy within the cell. It can also be the concentration of reactants, the purity of reactants, the type of electrodes, and all sorts of things can make a little bit of a effect on this, how much energy is required in the cell. So typically, rather than it just be the exact value of reduction reaction minus the exact value of the oxidation, we sort of say it needs to be greater than that. So if this summed value, reduction minus oxidation, that's one volt, we would say it needs to be at minimum 1.01 volts, or at least a minimum of 1 volt. Just a little bit extra to ensure that we get that reaction occurring. So if you have a look at this question, this is a bit of practice, just doing that little sum as well. So pause the video. I want you to work out the half reactions occurring. Write down the E0 values that correspond to those half reactions and work out what the minimum voltage is that would be required for this electrolytic cell. Okay, so we have, lead ions, bromine ions, carbon electrodes in a solution of water. Okay, all our possible reactants. According to your series, highest reaction in the forward direction is the lead undergoing reduction to form lead solid. So we would make lead in this electrolytic cell. And the lowest reaction in the reverse is our bromine ions undergoing oxidation to form bromine. Generally would be a liquid in this situation. Now, our E0 value of our first reduction reaction is -0.3, and our oxidation plus 1.09. And what I want you to look at is just go back. It's the same sum as we've done for all of our potential differences, so it doesn't make any difference. You should get, though, a negative value because we're not producing a spontaneous reaction here. We are requiring energy. So how much energy is required? Negative 0.13 minus 1.09 we're looking at here, and we get a value of negative 1.6 volts. So in theory, we would need at least 1.23 volts to obtain to allow this electrolytic reaction to occur, or at minimum 1.2 is what you want to be clear of. Okay, Some of the different chemicals that we can obtain from electrolysis: sodium, aluminium, chlorine, sodium hydroxide, and electrorefining of copper. We're going to have a look at some of these cells. Now, there's no need to feel like you need to learn all this specific details. It's more an understanding of, okay, so if we want to produce sodium, what, according to our series, does that mean our cell needs to consider? So that's the first one we're going to look at. Okay. So if we are producing sodium and if we are producing chlorine, as we went through earlier, we do need a molten cell. Okay, we do need water to be not in the equation, because in both situations, water is a stronger oxidant than the sodium ions, and water is a stronger reductant than the chlorine ions. So we do require molten sodium chloride, and that concept is something you do need to understand and be aware of for your SACs or for your exam as well. All right, so this is the half reactions we actually went through just a little bit before. Okay, the overall full equation, as you would write it, showing sodium ions and chlorine ions in a liquid form, and generally sodium liquid, because our cell would still be under higher temperatures, and chlorine in form in its gas form as normal. So in industry, this is what's called a down cell. What's really significant about this cell, what needs to be really carefully designed, is ensuring that the products at the two electrodes, so the sodium liquid and the chlorine gas, do not come into contact, because I'm sure you could probably imagine that what you've then made is two very reactive substances that, if they do come into contact, we're going to get a very, very spontaneous reaction with a large amount of heat energy produced that would severely damage the cell. So it's in their down cells are designed to ensure that are kept very separate and do not come into contact with one another. We can also have aluminium extracted, which, once again, aluminium is a difficult metal to obtain in its pure form. Effectively, any of these metals under here, anything that is below water, because of the really low strength in terms of electrolysis, all these metal ions are not very willing to react and reform these electrons and form their solid states. Okay, so basically anything below here you're going to find are difficult to obtain in their normal form. So we do need to require some form of electrolysis to obtain sodium and calcium, potassium, and so on, and aluminium. And when we do so, water cannot be involved in that half reaction. So you don't need to, once again, know this half reaction, all these reactions, absolutely not. It's more of an understanding, as I went through before, why we do have to extract aluminium. Why we do have to extract aluminium, and that it needs to be done out of the presence of water as well. If you are asked about any of this sort of information, you'll be given half reactions involved. It's not a very common thing that has been on exams though. We can also have a cell producing chlorine and sodium hydroxide, so not sodium, but also the production of chlorine is quite a common chemical and used chemical in lots of industries. So I'll just flick to the next section. So what we're looking at is a aqueous cell once again. Okay, so water is present within this solution. We have water, sodium ions, and chlorine ions. Okay, so it's not a molten cell, and therefore, as we went through before, the water here is a stronger oxidant than sodium. Okay, so we're not producing sodium, but that's not the desired product of this cell at all. So water will undergo reduction here. Undergo reduction at your cathode. If we have a look at the anode, as we looked at for the series, I'll just bring it back up so everyone's really clear. We're looking at these two half reactions here and how similar they are in strength. Okay. So water can oxidize and technically will, according to the series, in preference to chlorine. Rather than run a completely molten cell, which is very, very costly because of the amount of energy required to maintain that molten electrolyte, instead, the amount and the concentration of the H2O in solution is manipulated. Okay, so rather than necessarily having 1 molar H2O, what you can manipulate is having really high concentration. So high concentration of chlorine ions and low concentration of water. Low enough that we're still using water and still got a movable electrolyte, because that's still important. You still have to have ions being able to flow between your anode and your cathode just as normal. But it's sort of a balancing act. What that will mean is that particular order on the series, that water is more or water is stronger, kind of isn't necessarily what's going to occur anymore. What will happen is, because there is a large amount more chlorine present in the solution, within the cell itself, chlorine will preferentially oxidize and we will get a large amount of chlorine. We will still get oxygen produced 100%, but in this case, the setup of this cell is more economical and more favoured in industry, predominantly based on cost and things like that. Okay, so higher concentrations of chlorine allows that chlorine reaction to be more favoured. So we'll get chlorine gas also forming. Okay, so that's get another cell that produces your chlorine, just not necessarily at really high costs as you would if you had a molten cell. And I think this is the final anode, cathode, and your overall equation, in where you technically will get chlorine gas produced in a aqueous solution that's also has the presence of sodium ions and hydroxides. Hence, you're able to obtain sodium hydroxide as your second byproduct, which also can be used in industries for various different reasons. So chemicals, even the hydrogen as well, that can be used and sold. The last concept is looking at electro-refining copper. So what this process is basically using electrolysis to remove any impurities that might be within a sample or a plate of copper, if you will. Okay, and that's pretty normal when metal is mined from the ground. Metal is not mined in pure form, it's mined in an ore form, which is a mixtured form with other substances, generally other metals present within that ore. Some of those metals are useful, some of them are not so much useful, and it really depends on where it's mined from and so on. So if we have a look at what is actually chemically going on here. Okay, so once again, we are getting, we have our impure copper anode. This was what we started with, okay? And this is undergoing oxidation, okay? So it's undergoing oxidation at the anode. It is, you can sort of see it sort of degrading away here, and we're forming copper ions in solution. What this is also representing and showing you based on the series is we will also get the oxidation of other metals off that impure substance. So there might be nickel, zinc, gold, silver, all sorts of other things that will also be forced to oxidize into solution. So you get a number of metal ions occurring in solution. But according to your series, what then is our stronger oxidant in this case to reform into a metal is copper solid. And those copper ions will then have the greater strength than any of the other metal ions to reform with 2 electrons and reform copper solid onto our cathode. Okay, so basically what we're kind of doing here is what we're going to look at in our next topic, which is electroplating as well. Electrorefining of copper and electroplating of copper is quite similar, and we will do an experiment where you'll actually be able to do this as well. So unreactive metals are left in iron, and any of the very, very unreactive down here in the mud sludge, which is potentially can be used for other purposes that might be able to isolate out certain metals. All right, so that is the end of part 2, and we will look at electroplating in our next lesson.